Guys, I hit my head. I ran into a pole this weekend.
What are we doing now? We're just Chinese.
I was fishing with a friend, and we were walking alongside the pond. We were a little bit off the shore, and my friend got his wire or his like fishing line tangled. So I was watching him while we were walking, and I ran right into a no swimming sign.
Congratulations!
See?
You now know for sure that there is a sign there.
You don't see a red mark?
No.
There was a big red mark there. Totally just smacked right into it with that. Okay.
What I don't understand is why they put the lake there and they say no swimming. It's like, what? Why can't I swim in the beach?
Well, because there's no lifeguards, and so they're just trying to protect themselves legally.
Yeah.
Doesn't that make sense? Because what'll happen is someone will swim and they'll die, and they'll be like, "Oh, it's the state's fault."
Well, no.
Well, they could put up a sign that says swim at your own place.
Well,
That's still a sign.
I know, but still, like, as long as it's a sign, it's
No,
just
but
sure.
like,
It
if
said
you
no
say no
swimming.
swimming and then they swim, then you're not liable. If you say swimming, you're okay.
Well, they swim at their own place.
Okay.
Okay, my bad.
Okay, bonding pairs, lone pairs, electrostatic force, diatomic molecules. First of all, we should be all good on the diatomic molecules. What rule helps us with identifying the diatomic molecules?
7 on 7.
The 7 on 7 rule. So I will review this again because it's really important when we start writing chemical equations. Because if you write hydrogen as a lone hydrogen in a balanced chemical equation, you're going to be wrong. Okay? So it starts with the atomic number 7. If I were to trace this section, you would see the number or shape of a 7, and there are 7 of them. 1, 2, 3, 4, 5, 6, 7, and what? Hydrogen. So there's actually 8, so I call it the 7 on 7 rule plus hydrogen. You know, there's no other way of saying it. Okay? Electrostatic force. This is the force that this is the name of the force that holds particular atoms together within a compound. Okay? And it's electrostatic, it's got an electrical aspect to it. Okay? Alright, lone pairs, bonding pairs. So let's say I had a Lewis structure that looked like this. And you should at least remember this format here. Okay? These guys here would be called the lone pairs. And you could do any of these here. And this would represent the what?
Bonded pair.
Shared pair.
Okay?
Pair.
Just some vocab here that we should know. So if I use the word lone pair or use the words bonding pair, you guys should know what I'm referring to. Let's do some Lewis structures. Okay.
Do you forget that you're on video sometimes?
No,
He's just not using
no, I'm not easily embarrassed.
That's good.
He does not care.
I mean, I care, but I don't really care about that.
You can
I'm a caring person. Anyway. All right. So Lewis structure. Gonna be a 2D. Can't do 3D. Don't got a holograph. That would be cool. Just
Do it.
got show bonds between different atoms. So we're gonna talk about a single covalent bond, a double covalent bond, and a triple covalent bond. And some of you I'm gonna bore because you guys already know how to do all this, but I don't want to assume everybody does. Not everyone took physical science with me or took physical science at all. So, okay?
Wait,
I thought that's a recording.
you can graduate without physical science?
Somehow.
Wait,
Apparently.
I don't know. I don't think Brady West took physical science either.
He
did it in a homeschool,
Physical
though.
science and
Oh.
biology.
Okay. Yeah, I thought so.
Didn't take it through the school.
There's some sort of
You're like
weird
about something.
thing. Okay, so you guys remember when we did electron dot notation?
Yeah.
What do the dots represent?
Valence.
Valence electrons. Okay? So we're going to continue to do this, and we're going to show the octet rule. What's the octet rule?
8 of them outside, mostly.
Okay, things are stable most of the time when they have how many outer energy level electrons? 8. Okay, there are a few of them that are stable with less than 8. What are they?
Boron. The first 5.
The first 5, okay? And we're not going to worry about the transition elements or really lithium and beryllium because those guys are what? They're metals, and are metals going to form covalently bonded things?
No.
No. So are we going to do Lewis structures of an ionically bonded thing? No, we'll do something different when we show ionically bonded. Okay? All right, now we're going to get into the process of how this works. Okay, but essentially we know that an H2O molecule has 2 hydrogens with 1 valence electron, and an oxygen with 6. Okay? And again, we'll get into how we set this up to do this. I just want to show you what a single bond looks like, what a double bond looks like, and so forth. If you notice, I took the unbonded electrons from hydrogen and pointed them towards the unbonded electrons of the oxygen. I'm never going to split up a lone pair. Not in this class. In advanced chemistry, we do it a lot. But not in this class. We'll keep it simple. Cool? Okay? And when you have one electron from one molecule, or from one atom, sharing with one electron from another, we would call that our bonding pair, and we would represent it with a dash. That is a single covalent bond because it is just one electron from each element being shared. The Lewis structure of water, pretty simple. There it is. Now, would it matter if I put my lone pairs over here and my unbonded pairs over here and put the hydrogens this way and this way? Does that matter? No, that does not matter. Okay, so single covalent. Progress. Get to some more difficult stuff. I know you guys know how to do a lot of this stuff in review, so we're going to try. I don't want to go too fast, so stop me if there's anything that you're like, I forget, I don't know. Okay, let's see what happens when we're dealing with oxygen. Now I know I've been doing this a while, but I arranged it strategically like this. But if you look at oxygen, they both have 6 valence electrons, and they both have 2 unpaired regions. If something has 2 unpaired regions, that means it's going to have 2 bonds in order to make this guy stable. It's going to have to share both those electrons to get a total of 8. You with me, Gage? You look real tired.
No, I'm not tired.
What were you thinking
I
of?
slept.
What were you thinking of? Oh, you look like you were thinking about something else.
Oh wait, no, what was it? See? No, I was thinking about I was gonna take the test, these.
Oh.
I was thinking we needed.
Dude, that's on Wednesday.
Okay.
Good thing I got video footage for you guys.
Are we doing classes?
Probably. What do we only got? 1, 2,
Who's gonna answer the questions?
3, 4. Marty, Marty, cool dude. I just
That's like half of your class. What are we supposed to do?
That's not half the class.
Pretty much.
It's
A
the
third
only
of it.
people who talk.
That's what it seems like.
I was just gonna seem real quiet in here. What's these?
Yeah, like who's gonna answer questions?
Okay, so here's what I want to show you guys here. 2 unbonded regions means 2 total bonds. It could mean 2 single bonds, or it could mean 1 double bond. Okay? So here's how we're going to do this. We're going to see 1 electron from 1 will form a single bond. But notice we're still not stable because we have an unbonded region that needs to bond. Now some of you might think, oh, let's connect these electrons here, but we don't show it like that. That just looks funny. Okay, so do not take the electron from here and the electron from there and show a Lewis structure like that. Where do we typically show a double bond?
Next to the other one.
Yeah, we put the bond, even though we remove 1 electron, 1 unpaired electron from each, we actually show it like that because it's going to be, guys, the electrons are going to be shared in between the nucleuses of your neighboring atoms. Okay? Now, I like to rewrite this because I know that these are electrons and these are electrons, and we know that there's going to be an optimal repelling that goes on. So I'm going to keep these electrons as far away from each other as possible. Right? There's the angle here should all be about the same versus having a 180 degree angle and then 2 90 degree angles. You see that? So just get in the habit of trying to keep the electrons as far away from each other as possible. Does that make sense? I know we never wrote lone pairs in that location, but they repel each other, don't they? So they should probably be as far away from each other as they possibly can. Okay? Triple bond. Alright, now we got nitrogen. How many valence electrons does nitrogen have?
5.
5 valence electrons based on its location on the periodic table. Do we need a refresher on how to identify valence electrons? Anybody? All good? Now it's time to ask. Alright. 5. Now notice I took the lone pairs, and I kept them as far away from each other as possible because the bonds typically are going to be formulated in the middle. Okay, so notice I have 3 unbonded regions, okay, on each of them. Now I could form 3 single bonds. I could form a double bond and a single bond to get 3, or I could form 1 triple bond. In this context, we're going to form 1 triple bond. Remove 1 from each, form the single. Remove 1 from each, form the double. Remove the 1 from each, form your triple. Now remember, this represents how many electrons there? 6. Okay? But it's 6 that are being shared. Okay? So if I were to kind of just circle this nitrogen, and then circle this nitrogen, how many electrons are around that guy? 8. 6 of them are being shared, but a total of 8 around each of these nitrogens. That's really important because if you look at all of your guys within a Lewis structure and you can't find 8 total electrons around each, you probably have done something wrong. The only things that aren't going to act like that are going to be probably your hydrogens. They're stable with how many? 2. Following? All right?
So wait, if nitrogen is a diatomic element, why does it need 8?
Nitrogen isn't stable with 2.
But it's diatomic.
That means there's
That means there's 2 of them.
2 bonded together.
Ah,
Not like-
shoot.
Do you see why nitrogen can be stable, bonded to itself?
Yeah.
Because it can have 8.
Oh, so
but like
it
if I
needs 2
had,
of itself.
if I had, let me see here.
It still
Like if I were doing, I don't know, boron bond with itself to get 8. No. Okay? Now, let's get into the process here. Because we just did some very basic ones. Do you have this in your notes?
Yep.
Okay? Now I realize that we just did some very basic ones. We're going to get into more difficult ones. So we are going to do this guy. And you're probably wondering, how do I know what element goes where when I've got multiple? You're always going to have a central atom. Okay? So now, you're going to get to the point where you're not going to need this. This is just for help initially. Then you're going to get, I promise you guys we'll do this. You've done this enough in physical science. It probably should be coming back to you. And there's going to be a point where I cannot give you any new stuff. You'll have done it all. Okay, so there's only so many nonmetals up there, isn't there? And if I bond hydrogen with oxygen, wouldn't it bond exactly the same way as if I bonded hydrogen with sulfur?
Yeah.
Because they both have, oxygen and sulfur both have the same number of valence electrons. So if I bond hydrogen with oxygen and I bond hydrogen with sulfur, they're going to look exactly the same. Okay? So there's not a lot of things I can show you here that once I show you a few ways, you probably can do all of them. Okay? So it says write the electron dot symbols of each. All that's simply saying is kind of give yourself an idea of what it all looks like here. 4 dots for carbon, because that's 4 valence electrons. And 6 dots for oxygen. So that just kind of gives you a template for what you need to do. Now, I will show you this. You probably won't ever use this. You'll probably get to the point where you can do it pretty quickly. But it says determine how many valence electrons there are. How many total valence electrons does this whole thing have?
14.
1, 2, 3, 4, 5, 6, plus 6 more, 12.
Oh, I counted that.
Okay? Then it says place, this is probably the biggest thing that you'll need to remember. Place the element with a large number of what? Unpaired. Because you want the largest number of unpaired to be in the middle so that everything can surround it. Okay? Which guy up here has the most unpaired regions or unpaired electrons? Carbon. I've got, the max you can have unpaired is 4. So anytime you have carbon involved, it's in the middle. Every single time. Okay? So then what does it say number 4? Place that one in the center. Is that what it says?
Yep.
Okay, so you're going to take the guy that has the most unpaired regions, you're going to plop it in the center. Okay? Then what does it say next?
Place remaining element symbols around the central atom.
Okay, so I've got these two and this one that I need to place around. Doesn't really matter where it goes. Here's what I will say. If you have a lone pair here, don't put a symbol next to a lone pair because that lone pair is probably not going to break up. Okay? Thankfully we have all of these unbonded. So I'll put a hydrogen here. I'll put a hydrogen here. Does it matter if I put the hydrogen there or the oxygen? No, not really. Does it matter if I put it here or here? Not really. Okay? So I've just surrounded it, and then I'm guessing the next step says form single bonds.
And double and triple if necessary.
Okay? So let's start with single bonds though. Okay? We know hydrogen only needs to be stable with 2. It's got 1 unpaired, so let's bond it with 1 unpaired from carbon. Form a what?
Single.
Okay? Let's do the same thing here. Every time you form a bond, you should take an electron away from each. Now, as we look at this, we form single bonds between everything. Are we stable?
No.
Let's just look. If I were to circle around the carbon, I would have 3 bonds. Each bond represents how many electrons? 2, so I got 2, 4, 6, 7. Is it stable?
No.
How about this one? 2, 4, 6, 7. Is it stable?
Not quite.
Okay, so you can see here that I have an unbonded oxygen electron and an unbonded carbon electron. What can I form?
A double
A
bond.
double bond. Again, put it like that. Now we can check to make sure that we have 8 around everything except for hydrogen. Hydrogen is good with 2. So 2, 4, 6, 8. 2, 4, 6, 8. Stable? Everything's good? I think the last thing says, what's the last step?
Check counting on the total electrons.
Okay. 2, 4, 6, 8, 10, 12. Still got our 12 valence electrons. We didn't add any electrons. We didn't remove any electrons. We obeyed the first law of thermodynamics. Matter cannot be created or destroyed. Okay, now, there is a way that I could write this with the whole repelling idea, because we have 180 degree there, we got 90, and we got 90. So could I draw this a little bit better to show repelling?
Yeah, you go down a little bit.
Okay, so we'll go kind of at an angle here. I'll go like that, that, like that. I'll put those electrons as far away from each other as possible. That's about as close as you're going to get. Okay? Questions? How many of you actually did the last one without me? 1, 2. I do the last one, guys. I realize this is pretty simple. We will get into doing some polyatomic ions, which are more difficult, which we never did any polyatomic ions when you guys were in physical science. We will do resonance, which is a little bit more difficult. I want you guys to draw the Lewis structure of this, following your rules. I don't care if you necessarily show how you counted all the valence electrons. That's not a big concern of mine, as long as you understand the process here. Oh, I should have showed polarity. We'll go back when we're done here. Show polarity. You got it done? Wanna come check? Anyone done other than Trinity done? The last one.
Oh, what?
You're going ahead, aren't you? Oh, did I skip one? I skipped that, didn't I?
It's on the next page, turn the
You
page.
did skip it.
There's another one.
C2H2?
Oh, yeah,
That's
you
the
did
one.
skip that.
I skipped C2H2, sorry.
Probably started with a compound.
Yep. Yep, easy peasy. Yep. Yep. What do we got? 3 chlorines, not just one.
I like saying.
Okay.
I'll come over here.
Yeah, I did it.
Yep. Almost done? And close? Yep.
Wait, why'd you skip?
I didn't know it was there.
Too high.
So there I just put the carbon as a central atom, the surrounding elements. Now notice I put the lone pairs, not lone pairs, the unbonded pairs next to each other, strategically. Okay? Get it? Okay. Lynn, how you doing? Okay, I think you put not the correct number of valence electrons around chlorine. So look up here. So chlorine has 7. And I strategically put the unbonded pairs next to the unbonded of my central atom. See that?
Yeah.
Okay, so each of these has 7. So they only need to bond 1 to be stable. So take one, form a single. That has 8 now.
Okay, how do you always want to put in the center?
Number 3. What does it say?
Oh, large center unpaired, okay.
Yeah, this one has 4 unpaired. That one had 1 unpaired, 1 unpaired, 1 unpaired, and 1 unpaired.
I thought it just meant large center of
Of electrons? Yeah, no, unpaired. Yep. You should get this. Now, let's do polarity here.
Make the bond of hydrogen a bit longer.
Now, we're not going to mess with well, I see what you're saying. Okay, we're not going to like kind of show the electrons being tilted one way, but we can show what the result of that is going to be. Okay, so chlorine and chlorine are going to pull opposites each other, right? So technically chlorine is going to pull upward and upward, but they're going to be opposite. So really, this would be negative and negative. So do you see how that is not opposite regions of charge, is it?
No.
It's opposite regions, but not opposite charge. Okay?
Carbon serves both.
But this one pulls more than carbon, so that would be negative, right? And which one pulls more? Carbon or hydrogen? Carbon just a little bit, I think.
Really?
Well, it's not that much.
No,
Even-
because hydrogen is that big and carbon's bigger. So
I don't know exactly.
Yeah.
We're really close. But regardless, this chlorine is going to kind of almost pull everything that way because it's got a really strong electronegative pull. So what you have here is your polarities created here. These really just cancel each other out. Okay? Let's do the one that's a little bit simpler. We just did this one earlier. Okay? Oxygen is the second most electronegative element that we have. So it's going to take and pull electrons that way, making this negative. Okay? Because it's so electronegative, it's going to start pulling everything that way, exposing these nucleuses, and there's your positively charged. There's your polarity on that guy. Okay? Questions? Alright, we're done. Look at some more difficult ones
Where's the whole?
tomorrow.